This conference will now be recorded.
Hello everyone. The topics that we are going to discuss today: placement of elements based on electronic configuration, classification of elements into blocks, and there will be different blocks: S block, P block, D block, and E block, and there will be related problems also. Okay, so let's start. How to arrange the elements based on electronic configuration along the period that we have already seen in the last class. Now we will see that each period one by one we will take, that is first period, second period, third period. In this way we will see one by one how we are having the elements in each period. Here we have the first period. Now it starts with filling of valence electrons in 1s orbital, and in 1s orbital maximum capacity is only 2 electrons. So that is the reason only 2 elements we have in first period. Okay, and when it is 1s1, the element is hydrogen. When it is 1s2, the element is helium. Okay, so that is all about the first period. Now the second period, it starts with the filling of valence electrons in 2s orbital, followed by 3 2p orbitals with 8 elements. Now as we have here the orbitals, one is 2s, another one is 2p. In 2s we can maximum place 2 electrons. In 2p maximum capacity it is 6. That means 2 plus 6, total 8 elements we can have in second period. It starts from lithium and it ends at neon, which is the noble gas. Now the third period, in third period we have 3s and we have 3p. Now in 3s maximum electron we can place 2 electrons, and in 3p we can place maximum 6 electrons. So again, just like the previous period, here also we can fill 8 elements, and these 8 elements, it starts from sodium. That is the first electronic configuration. For this period it will be 3s1, then 3s2, then 3s2 3p1, and in this way it will end at 3s2 3p6, and it starts from sodium, it ends at the noble gas, that is group 18, which is argon. When it is fourth period, now one orbital here we have extra. In fourth period there is 4s, there is 3d, sorry, let me write it clearly. We have 4s, we have 3d, and we have 3p. It is 4p, not 3p. Okay, now in 4s maximum we can have 2 electrons, in 3d we can have 10 electrons, and in 4p again we can have 6. So in third period all these orbitals are gradually fulfilled. So in this period only this D block is basically starting. The first period, the third period, the second period, there is no D orbital present, though it is third period, but 3D is not present in third period. 3D is present in fourth period, and this is according to above principle. So the fourth period starts with filling of valence electrons, just like the other periods. It is also from 4s. Now after 4s orbital, followed by 3D and 4p, and it is not just accidental, it is based on above principle. So after 4s it will be 3d, which is filled, and this is all about this D block. It starts with, that is the, I'm now focusing on 3d. If you consider 4s, the first element is actually potassium and then calcium, but if you consider 3d, it starts from scandium, and that is actually group 3. It ends at zinc. So this part is only the D block part, and here it is group 12. Then after 12, it's which group starts? It is 13, and then up to 18. So after 4s, this is something new you are seeing, because in first period, second period, third period you have not seen this. In fourth period we are seeing this first time, that 3d orbital is filled. Now 2 10 6, 2 plus 6 8, and then again 10 you have to add. So total 18 elements can be present in fourth period. Out of these 18, 10 elements are actually in 3D orbital, and that is why it is called fast transition series. Because transition series, why? Because 3D is basically not just 3D, any D, that is if you consider D block, that is actually present between S block and P block. So that is the reason these elements for D orbital, that is D block basically, they are known as transition elements. Now as this is the first D orbital filling, first mean I mean to say 3D, because when it is second transition series in the next period, that will be 4D, and then the third transition series, that will be involving 5D. So as it is 3D, the first D orbital is filled. This is the first transition series starting from scandium up to zinc. So these 10 elements, they are having this specific name. They are present in D block. But overall, how many elements we can have? It is 18. Next, after fourth period, fifth period. So here principal quantum number is 5. Now just like fourth period, here also similar to fourth period, it also starts with filling of valence electrons starting from 5s, and after 5s, in the previous case what you have seen, after 4s 3D, now after 5s it is 4D, and then it is 5, sorry, it is 5p. Maximum electrons you can have 2, here you can have 10, and here you can have 6. And just like 3D, you have seen it starting from scandium up to Zn. Here it is starting from yttrium. It is ending at cadmium. Now these 10 elements, just like the previous 3D 10 elements, we have given the name first transition series. Now the name will be second transition series. Okay. So 2 plus 10 plus 6, total 18 electrons we can have. That is 18 elements we can have, because we can maximum place 18 electrons. The first 2 elements in S block, next 10 elements in D block, next 6 elements they are in P block. Sixth period, there are total 7 periods. Now we have already finished 5. Now we are starting 6. It will also start from 6s, but now one orbital which you have not seen before, it will be introduced. After 6s, there will be next, which orbital will be filled? It is 4f, then 5d, then 6p. So this s and p, this is common, that you have already seen in second period, third period, but now this is new, right? Now in 6s, as we know, we can have 2 elements. In 4f, there are how many elements we can place? 14. 5d, 10, not 5d, any d. And for p, it is 6. So now it is not just 18, it is basically 14 more elements you can place. Okay. So in 6th period, filling of valence electrons start with 6s, and then following above principle, next filling happens in 4f, then 5d, then 6p. Now the filling of 4f orbitals, it begins with cerium and it ends at lutetium. Now starting from cerium up to lutetium, here this part, it is actually present as a block, and they are also known as fast inner transition series. Why inner transition series? Because here this 4f, if you consider the principal quantum number, that is 6. So 4 is 2 less than 6. That means if principal quantum number n, then which f is filled? It is n minus 2. So that is, it is known as inner transition, not just transition, it is inner transition. And as before cerium, there is La having atomic number 57, and that is the reason here, based on La, the first member of first transition inner transition series, their common names, that is together all these elements together we call it lanthanides, and that name is based on La, lanthanide. So here we are focusing only these 14 4f elements, because 6s, that is S, D and P, how they are filled, that we have already seen. But in 6th period, which we are saying new, it is f orbital. Which f orbital? It is a 4f. The first f is 4f. There is no 3f, there is no 2f, right? Now after this, the last period, 7th period. Now 7th period, it starts with obviously 7s, and as you have seen in the previous case it is 6s, next 4f, but now 7, that means principal quantum number n, so n minus 2, that must be 5. So now it is 5f, just like 4f you have seen in previous case. Now it is 5f. After 5f, previously we have seen 5d, now it will be 6d, and then there is 7p. So again it is 18 plus 14 maximum. This is the number you can have, this number of elements. So here 5f orbitals are filled, just you have seen previously 4f orbitals are filled, cerium to Lu, or you can say La to Lu, that is lanthanum up to lutetium. Lanthanum is 57 atomic number and lutetium is 71. And here in case of that is 5f orbital, it is also known as 5f block elements. These 14 elements together we call them second inner transition series. Here the first element is basically Ac, having atomic number 89. Sorry, yes, it is 89, and then it ends at lawrencium, having atomic number 103. Okay, so just try to remember atomic number for the first element and the last element. And after Ac there is thorium, having atomic number Th90. Now these two blocks, that is 4f and 5f, these two inner transition series, or you can say these two A block, we place them separately, not in the periodic table. If you directly look at the periodic table, you will see there is 4s left hand side, and sorry, not 4s, I mean to say S block in the left hand side, P block in the right hand side, and in the middle part there is D block. You will not see F block. F block is, it is present at the bottom of the periodic table. Okay, it is placed separately. Now if you want to know why it is so, because if you place it after 4s, then the periodic table, it will be very wide, and it is difficult for day-to-day life to handle that type of periodic table. So just for sake of convenience, so that we can handle it easily in day-to-day life, we have placed them in the bottom of the periodic table. Okay. Now variation of electronic configuration in along the period, that we have discussed in last class, but now we will see how it will happen if it is in the group. We know there are total, how many groups? Total 18. Total 18 groups are present. Elements of group have similar electronic configuration in the outer shell. So this condition you will always see. Having same number of electrons in the outer orbitals, they will have same type of properties. So that is why they are in same group. Group means what? Suppose in general, if you consider the word group, what it means? Whatever members will be present in group, they should have similar type of property. So that is why in this case also, why we have placed all the elements in same group, because they are having some similarity in their properties. Okay, that is the reason. So here you can see it is expressed as simpler way as possible. Group number 1, and then it is ending at group number 18. So for group number 1 and group number 2, these two together, it is actually S block. So they are known as S block elements. Their electronic configuration is most simple in the whole periodic table. If you consider, it is very easy to remember. NS1, NS2. So NS1, remember lithium, sodium, potassium. What is the electronic configuration? 2s1, 3s1, 4s1. Then NH2, that is the group 2. Remember magnesium, calcium, 3s2, 4s2. So they are having same type of properties, that is magnesium, beryllium, calcium, they will have some similarity in their properties. Now after these two groups, just go to the right hand side, that is starting from this up to this part. This is actually P block elements. Okay, how many groups are there? Total 6 groups, because it starts from 13, it ends at 18. Okay, so total 6 groups are present, and in between these two, that is S block left hand side, P block right hand side, in between these two there are these starting from 3 up to 12. All these are present. Okay, so 2 groups here, 6 here, and in between these two there are total 10. Okay, now let me erase all this. For group 13, here only ns and np, these two are in, and the last electron is entering in the p orbital, and that is why they are in p block elements. Fine. So ns2 np1, just add these two numbers, you will always get, that is, this is the valence electron, you will always get the last digit of the group. So in this way you can easily remember from valence electron what should be its group. Suppose just take oxygen. How many valence electron? It is 2s2 2p4, so 6 valence electron. So it should belong to which group? 16. That is the last digit. So this last digit is always it is denoting the number of valence electrons. Similarly for noble gas also, total 8 valence electrons are there. So it is starting from the configuration ns2 np1, then 2 3 4 5 6, maximum capacity fulfilled. Okay, now what about d block? In between these two extreme we have this d block, and in this case starts from ns2 n-1 d. So after ns2 the next electron it is entering at 3d. Sorry, 3d is actually for the fast transition series, but in general what should I say, it is n-1 d2. So ns2, n is the principal quantum number, then the d orbital it must be the n-1. That means if n principal quantum number is 4, n-1 d means 3d. If principal quantum number is 5, that means 5s, which d is present corresponding? It is what I have said, 5s. That means 5 minus 1, it should be 4d. So it is always 1 lesser than the principal quantum. So that is why nh2 n-1 d1, then 2 3 5 5. Now here why it is so, that you already know, because we know what is half field stable configuration. What is the importance of that we have seen in the last unit. So as after d3, normal expectation is it should be ns2 n-1 d4, but why it is 5? It is because half field configuration is preferred. So that is why it is not d4, it is taking one electron from this so that it can become d5, which is half field stable configuration of d orbital. So that is why this exception here, this you can also find this exception in group 11. So two most common example that we give is, one is chromium, another one is copper. So this related to this discussion we have seen in the last unit already. So in this way all these d block elements is fulfilled. Now what about a block? Actually a block, it is part of group 3 only. So all these elements in 4f for lanthanides, 5f for actinides, all these 14 elements that are present. If you consider the first member, that is La, which is present somewhere here, and Ac, based on which we have this common name lanthanides. From Ac actinium it is actinides. So La and Ac if you consider, it will be total 15 elements. But why we have placed them here? Because if you place it in the periodic table directly, because all these 14 elements are actually part of group 3, so the periodic table will be very wide, which is difficult to handle. So that is why it is separately placed bottom of the periodic table. Look at the configuration: 6s2 4f 1 minus, sorry, not 1 minus, 1 up to 14. So this is the maximum capacity. Gradually from 1 it will be filled, 1 2 3 4 like this. And when it is 5f, it is starting from 0 to 14. There is a slight difference in the electronic configuration, but more or less it is same. Okay, so now you know why they are placed in the bottom of the periodic table, not directly in the periodic table, because in that case it will be very wide, and all these elements they are actually present in group 3 only. Okay. Some groups can be combined as S, P, D and A block that we have seen already. So these two groups 1 and 2, they are under S block. Group 13 to 18, they are under P block. And then we have A block, though in case of A block all are from same group, it is group 3. But if you consider D block, then there is 3 up to 12. But how many blocks are there in the periodic table? SP, D and A block elements on the basis of, and it is based on what? It is basically based on the fact that the orbital in which the last valence electron is entering. So if I am saying any element from 4f, the last electron must be entering 4f, that is F orbital. If I am saying anything from D block, the last electron is entering D, that is why it is under D block. So this is the statement, that is the last electron, it is entering which orbital, because based on that it will be belonging to that particular block, S, P, D or F. Fine. So see, this is an imaginary periodic table. It is not the actual modern periodic table. Why I am saying imaginary? Because A block is not part of, it is not placed directly in the periodic table. But as I have said, they are part of group 3. So see, after group 3, there is a block and then it is group 4. But if you place it in this way, it will be very wide. So that is why this total part, we have brought it in the bottom of the periodic table. 4f, just below it 5f. Okay. So now it is a very simple picture of where you can focus on all the blocks. Not all the elements are present, only the blocks are highlighted here. Group 1 and 2, S block configuration starts from ns1, it's an ns2. Then transition element, it is from 3 to 12. General electronic configuration ns1, or sometime it is 2, because there are 2 exceptions in case of chromium and copper, remember. So in that case only it is it may be 1 or 2. So here you can see n-1 d 1 up to 10. So it can start from 1 and it will end at 10, and then it is 1 ns 1 to 2. And then for P block it is ns2, then np 1 to 6. No change in ns2, but np, it is starting from 1, it is ending at 6. And for A block, general electronic configuration, it is ns2. Now ns may be 6s or 7s, 6 period and 7 period, and n-1d. So for 6, when it is 6s, n-1d is 5d. When it is 7s, n-1d is 6d. It may be 0 or 1, and n-2 may be 4 or it may be 5. So this is the actual periodic table. Though I have presented this picture before. Here from different colors you can understand the nature of different types of elements. And this is 4f, this is 5f. So see, if you just focus on these two part, 57 La. So after barium, S block 56, we know as we move it is one atomic number increasing gradually 1 by 1. So after 56 it is 57, that is fine. But see, after 57 it is hafnium, which is 72. So all the elements in between 57 and 72, that is starting from 58 and 71, all these elements are basically in between La and HF. Okay. Similarly, just come to the next period, 89 after 88, that is fine. But after 89, it is 104. So between 89 and 104, all these elements starting from 90 up to 103, all these elements are present in between AC and RF. And these are known as 5F. We have placed them separately in the bottom of the periodic table. So these two parts you have to focus if you want to know what is A block elements. Okay. Now there is some two things that we should mention in the modern periodic table where there is some controversy. Helium, it should be in the S block. Why I am saying so? Because its positioning in the P block along with other group 18 elements, it should be belong to S block. It should be in S block, but why I am saying so? Because it has configuration 1s2, which is matching with the configuration of group 2, that is ns2, right? But why it is placed in group 18? There are some separate reasons for this. So helium should belong to S block, but its positioning in the P block along with other group 18 elements. Its positioning in the group 18 along with other 18 elements, other group 18 elements. Why it is justified? Because it exhibits properties like other noble gases. Other noble gases means neon, argon, krypton, like this. And we know that from any up to this, I'm not considering this because it is not very stable. We hardly talk about OG. Okay. So in case of these noble gases starting from neon up to Rn, if you look at the configuration, it is NH2 NP6. So directly there is no similarity with helium, but the similarity is basically because of this field valence shell. Okay, so that is why we have placed it in this part, that is along with the noble gases. Fine. Next we'll see another controversy, hydrogen. So the first point is related to helium, the second point is related to hydrogen. Hydrogen has only one s electron, one s1 configuration, and hence it should be placed in group 1. That is the logic. But if you consider another logic, that as it is 1s1, it can attract one more electron. Now it will become 1s2. So it can gain an electron to achieve a noble gas arrangement like helium. Now this type of observation is common for group 17 elements. If you consider F, it has configuration 2s2 2p5. It can attract one more electron and now it will become the configuration of neon. So just like that, you can also expect the same thing from hydrogen, that it will take another electron and then it will become 1s2, and just like helium. But it is not that. That is, we are not having hydrogen in group 17, rather we are having it in the first group along with the alkali metals. So hydrogen, though it has one electron and hence we can expect it in group 1, but another logic that it can gain electron just like group 17 elements, which is halogen family, common configuration NH2 NP6. So between these two logic, it is which one is given priority? It is the first one. So it is placed along with the alkali metals. So these two are the controversy. One is related to helium, another one is related to hydrogen. Fine. Now one by one, if we focus on the blocks, the first block is S block. Here the last electron is entering S subshell. Here the last electron is entering S subshell. General valence shell electronic configuration is either NS1 or it may be NS2. So when it is NS1, when it is group 1, then it is NS1. When it is group 2, then it is NS2. So that is why general valence shell electronic configuration for S block NS1 to 2. Two groups are involved, 1 and 2, that you can see in the right hand side. The group 1 elements, they are called alkali metals, while the group 2 elements, they are called alkaline earth metals. Fine. Now details we will not discuss here. That is basically that belongs to separate unit, which is S block and P block unit. Okay, not here. The S block metals, they are very soft in nature. Even you can cut them with a knife. They have low melting point and low boiling point. Now it is not that only S block they contain metals. You can also find metals in D block. You can find it in P block. But though all are metals, there is some basic difference. So when we are talking about the metals of S block, there is some specific property, and the properties are that they are soft and they are having low melting point and boiling point. Now these metals are very reactive. They are very electropositive and they form ionic type of compounds. Only exception is these two. For first member of both the groups, there is some difference. Okay, but except these two, for other elements, starting from sodium to francium, from Mg to Ra, all are they form ionic type of compounds. These metals lose their valence electron to form cations, making them strong reducing agent. Now as they are very highly electropositive, having electronic configuration NS1, NS2, now they can easily lose these electrons, because when they lose this electron, they achieve the previous noble gas configuration. Just take the example of Na. Electronic configuration after neon, it is 3s1, but if it is losing this electron, it will achieve the stable configuration of neon. So that is why they can easily, that is, the process is very facile. Fine. So they can easily lose this electron. That means they can be a good source of electron. So that is why they are strong reducing agent. Because of high reactivity, they are never found in pure condition, that is in elemental form. What I mean by elemental form? That is just in form of Na, or suppose strontium, in the form of strontium, you will never find them. Why? It is because they are very reactive. They will always react with some other elements. They will always try to give electrons, because they can easily lose these electrons. So in this way, they are very reactive. They will always make some compound. They will remain in the compound form, not in pure form, or you can say in elemental form. Okay. And as they are very reactive, you will see the sodium potassium metal in the laboratory, they are always kept in oil, because if you keep it open, it will catch fire. Next is P block. Now in P block, it starts from group 13, it ends at group 18. Total 6 groups are there. The last electron enters in P subshell, and that is the reason we have all these elements in P block. Groups involve 13 to 18, electronic configuration NS2NP1 to 6. So for 13 it is NS2NP1, then for 14 it is NS2NP2. In this way, up to group 18 it is ending at NS2NP6. These block together with S block elements are called representative elements or main group elements. So just imagine the periodic table, S block left hand side, P block right hand side. These two blocks together you can call representative elements or main group elements. And just focus on these two groups. Group 16 elements starting from oxygen up to polonium, they are called chalcogens. And group 17 starting from F up to astatine, They are called halogens. Okay. The elements of the last group, that is group 18, they contain completely filled valence shell configuration NH2NP6. So that is why they have no tendency to take part in reaction, because they are already satisfied with their electronic configuration. It is fully filled. So they can be found in pure form very easily. Remember in S block what we have said. It is difficult to find them in pure state because they are so reactive. And just this is, if you consider noble gas elements, it is the reverse case. Now, as they are very satisfied with the electronic configuration, they are very inert in nature. That is why they are called inert gas or noble gas. And another very special fact about P block, it is the only block that contains 3 different types of elements: metals, non-metals, metalloids. Metals you have seen in case of S block, there is no non-metal, there is no metal. But if you look at this, here you can find all of them. Okay, so here this color, that is the orange color, they are basically denoting the metalloid, and the green color BCN, all these are basically non-metals, and metals are basically in light blue color. Fine. So as there you can find 3 different types of elements, so that is the reason they can make chemical compounds by different ways. They can lose electron, just which is the property of metal. You have seen it in case of group 1 and 2. They can gain electron, which is the property of non-metals. Though I am not saying that non-metals they always gain electron. It depends, because it is not that all the non-metals are having same type of non-metallic nature. There is some high non-metallic nature or low non-metallic nature. So depending on that, sometimes there may be sharing also. But I am saying mostly the predominating feature is there is a tendency to gain electron, because they are non-metals, they are highly electronegative, and there may be sharing of electrons also. Okay, and so different types of chemical properties you can find in P block, and it is very versatile. Now compared to S block, which is very easy to predict, because there is some common property. All are metals, obviously you can expect them to behave in a particular pattern. But in P block you have so many different things: metals, non-metals, metalloids. So obviously their chemical behavior will be more enriched, more versatile, okay, compared to S block. D block starts from 3 up to 12. Valence electrons are now entering outermost D subshell. Okay, so that is the reason we are having all these elements under D block. General valence shell electronic configuration NH1 to 2. Basically it should be 1:2, but there are exception. For first transition series, these exceptions are found in these 2 elements. So because of these exceptions, it is the general configuration where you will say it should be like this: NS1 to 2, then N-1, D 1 to 10. Okay, they are found in the center of the periodic table. Now that you have already seen, and their properties are intermediate to that of S block and P block, and that is the reason we call them as transition elements. So don't call them main group elements. That is reserved only for S block and P block. So these, in between these two, we have D block elements, and they are called transition elements. These elements also show more than one oxidation state. So different oxidation state you can see, and that is why their chemistry is not so easily predictable, unlike S block. In S block, it is very easy to predict the chemical properties, because there are common oxidations. There is some specific oxidation state, +1 for group 1, +2 for group 2. But in this case, because of this variety of oxidation state, here chemistry is also not comparatively complex if you compare with H block. And they form ionic compounds, covalent compounds, as well as coordination compounds. We are not going into the details because they will be discussed in the respective units. Okay. So primary idea I can give you that when it is ionic compound, it is basically complete loss of electron from one element and complete gain of electron from the other element. Then it is ionic compound. There is generation of positive charge, generation of negative charge, and there is attraction between these two opposite charge. But when it is covalent bond, it is basically sharing of electrons. It is not one is given electron completely, another one is accepting completely. No, it is not that. It is sharing of electrons. So that is why it is covalent. And there is coordination also. So in coordination, electrons are coming only from one element. But once it is, the process is done, now it is shared between these two elements, just like covalent. So these are the different types. All you can have, you see, in D block elements. They have high melting point. This is what we have seen in case of S block. Remember, here we have seen that their melting points low, but now what is mentioned, melting point high. So this is difference. They are good conductors of heat and electricity. A block, part of group 3 elements. Remember, after La we have all the 4F, after Ac we have all the 5F elements. So part of the group 3 elements have their valence electrons in inner F subshell. Why it is inner? Remember, I have already mentioned. Again I am saying, if principal quantum number is n, suppose if it is 4, sorry, actually it is not 4, it is either 6 or 7. So let me take it as 7. So the inner F means it is n minus 2. That means it is 5. So when n is 7, it is 5. When n is 6, it is 4. Fine. So here the electrons are entering either in 4F or in 5F. So that is why they are A block elements. And they are known as inner transition. Okay. There are two inner transition, first, second. So two series are present. The first series, the name, common name we use for all these elements, lanthanides, which is based on La, because all these elements are basically following lanthanum. And the elements thorium up to lawrencium, they are actually following Ac. So thorium, it is starting from atomic number 90, but the previous element is basically Ac 89. Cerium, it is 58, previous element is La. So as they are following La, their names are lanthanides. Thorium to lawrencium, they are following Ac. That is why their names are actinides. Okay. General valence shell electronic configuration. For the first one, it is 4F starting from 1, sorry, it is 1 to 14. It should be 14. Then 5D 0 to 1 and 6S2 for actinides. Now it is 5F 0 to 14, not 1 to 14. And in case of 6D, it is 0 to 2, not 0 to 1. There is a subtle difference. They are placed at the bottom of the periodic table. These elements are also metallic in nature. They are having high melting points. Now in this case also, you can see variable oxidation state, though the variation is not so high in as you see in case of D, but there is also variation. And special points for actinides is that they are highly radioactive elements. Okay. So especially we will see in case of actinides, we generally our restrict or discussion the first 4 to 5 elements, because the more you move towards right hand side, the more is the radioactivity. Okay. Now we will discuss this question based on whatever we have discussed until now. The element with atomic numbers, one is 101, another one is 104. So these two atomic numbers given, you have to find. They belong to respectively. Look at the options. For the first option, it is saying that 101 atomic number, it belongs to group 11. 104, it belongs to group 4. Then the second option and also the third option, 101, it belongs to actinoids. but 104 belongs to fluoride 6. Then for the last option, 101 is from group 6 and 104 actinides. So basically, here which element, that is not important, you just have to know their position. So how to answer this type of question? So you have to remember these two things. What are those two things? The first is you just have to remember all the noble gases and in which period they belong. So remember starting from helium up to Rn, and also you have to remember their atomic number 2, 10, 18, 36, 54, 86. Now it is not very difficult to remember because just add 8 to helium, you will get 10. Then add 8, you will get 18. So 8, 8. So next you have to add 18. So in this way, you can proceed as you are moving down. Okay, so just remember 2, then add 8, 8. Or if you directly remember, that is also fine. It is up to you how you want to remember. Okay. Now once you have remembered it, how you will proceed to answer the question. Atomic number, take the first one. It is 101, 101. First point, what is the last noble gas? It is obviously 86. That means it is period. Which period? It is 6 period. Now obviously this one 6 period is already complete at Rn. So 101, it must be in the next period, that is 7 period. Now Rn, it has the last electron in 6p. That means 6p is already filled. Now you have to take the help of up-bound. After 6p, the next orbital where electrons are present, it is 7s. After 7s, it is 5f, right? Now 86 and 101, you just have to check that if you subtract this, then what number you are getting. Okay, so based on that, you will be able to understand in which orbital the electron is present. Okay, so it is basically 15. So after Rn, 15 more electrons you have to place. So in 7s you can place maximum 2. That means 13 more electrons are there left. So these 13 electrons, that must be in 4f, 5f, because 5f capacity is 14. So 13 elements it can be present. So it must be from actinoids because it is 5f elements, right? Now what about the next atomic number 104? Now 104 means 3 more electrons are present. There is after 15, 3 more electrons are present, and after 5f there is 6d, and then there is 7p. Now after 5f, 6d, 7p, and here you have 3 more electrons. Now you have option B and C, these two actinoids that we have already confirmed for 101, so you can cancel A and D. Now when it is actinoids, the next element 104, it must be from group 4 or it must be from group 6. Now if you look at this periodic table, this is the position where 4f is starting, but our element, both the elements, they are actually from 7 period. Now from 7 period, first one is actinoid, that is already confirmed. See, you can also check it, 101. Which element, that is not so easy to remember. Okay, but the next 3 electrons, it is 1 electron, 1 electron. That means here these 13 electrons you have already placed, right? Now the next electron, and the next. Now the next one, it will come where? It is, that is up to LR, it is already ended here. The next element is this one, 104. And remember, this is group 3, this is group 4. So you cannot say that 104 is from actinoids. Though in option you don't have that, but just check yourself. Suppose the options are not there, and 104, as it is 13 already reached, so maximum capacity 2 more electrons. So it should not, it cannot be in actinides. It should be after group 3, which is at 7 period ending at lawrencium, LR, atomic number 103. So it must be the next element. And it is which group? Group 4. So considering all these facts, you can say this should be the correct option. Okay. The characteristic of elements X, Y, Z. 3 elements are given. Atomic numbers are also given. For X it is 33. For Y it is 53. For Z it is 83. Different statements are there. X, Y, it is said they are metalloids. Z is metal. Then in option B it is said that only X is metal, Y is non-metal, Z is metal. 3 are having different characteristics. Option C is saying that all are metals. So basically what you have to do, you just have to know their positions. It is not directly asking, that is in the last case, it is directly asking from which group it is the element is. But in the question is now framed in a different way. But actually the basic thing that you have to do, it is just like the previous problem, same. So again you have to take the help of this novel dash. Okay, so 33, what is the last element? It must be 18. Now it is third period, that means it must be in fourth period. Now 36, 33, that means if it is 18, then 33 it must be from group 15, because after 33 3 more, 16, 17, 18. So if it is 36, 33 must be from 15. Okay, now 15 and which group, which period? Third. So it is not metal, it is not non-metal, because metal is the first elements, non-metal they are from the that is as you move down, metallic nature increases. So it is something in between. So that is why it should be metalloid. Then what about Y? 53. That means it is just before xenon. So it is somewhere here. And it is from group 17. It is halogen, and halogens are mostly non-metals. Then what about Z? 83. That means 86. It is also from group 15. It is somewhere here. Now it is from 6th period, that is as you move down in group 15, metallic nature increases. So considering all these facts, option B should be the correct option. You can also see, check it here. 33 metalloid, 53 and bismuth, and option B is the correct option. Okay, so we are at the end of the session and we will not proceed anymore. Thank you for listening.